Welcome to section 4.5, Bayes' rule. In this section, we'll learn how to update probabilities when new evidence comes in. This is one of the most powerful and practical tools in statistics, used everywhere from medical diagnosis to sports analytics to machine learning. Think of Bayes' rule as a way of saying, now that I know this happened, what does that tell me about what's likely? It's named after Thomas Bayes, an 18th century theologian and mathematician who first formulated the idea of conditional updating. We use Bayes' rule when we want to revise a probability based on new information. For example, if we already know a student has perfect attendance, what's the probability they're a Dean's List student? Or, if we observe someone flying through the sky wearing a red and gold suit, what's the probability that they're Iron Man? This is different from just calculating a basic probability. We're using evidence, something we've seen or learned, to update our belief about a situation. It's what doctors do after getting test results, or what your phone's spam filter does after checking if a message contains suspicious words. Bayes' rule helps us flip the direction of a conditional probability, going from the probability of A given B to the probability of B given A. Before we get into Bayes' rule, we need to understand the law of total probability. This law helps us compute the probability of an event A by breaking it into mutually exclusive pieces. Think of it as stitching together a full probability from different cases. Let's say that we are trying to calculate the probability that a student drinks smoothies, but we don't know their major. We can split the population into majors: business, biology, engineering, and so on. If we know the probability that each major drinks smoothies and the proportion of students in each major, we can combine those to get the total. So the formula looks like this right here. That's the sum of the probability of S sub I times the probability of A given S sub I, or written out longhand, right? That's what that capital sigma means, that repeated addition. For this example, the S sub I would be the major and the A is drinking smoothies. So we're multiplying the proportion of the first major times the proportion of that major who drinks smoothies, then add proportion of the second major times the proportion of the second major that drinks smoothies, and so on, right? Keep adding all the way through all the majors. Each term represents the contribution from one group to the overall probability of A. This total probability becomes the denominator in Bayes' rule. Here it is, Bayes' rule. It's the probability of S sub I given A is equal to the probability of S sub I times the probability of A given S sub I over the probability of A. This allows us to update our belief about the probability of group S sub I now that we've observed A. The numerator is what we already know, how common group S sub I is and how likely A is within that group. The denominator is the total probability of A, which we get from the law of total probability. Bayes' rule is like flipping the perspective. If you know the probability someone wears glasses, given they're a philosophy major, Bayes' rules lets you find the probability someone's a philosophy major, given that they wear glasses. Think of it as recalculating the odds once you've seen a new clue. Like when you see someone wielding a hammer and glowing with lightning, the odds that that person is Thor suddenly go way up. Let's work through an example. In a fictional Marvel survey, 30% of fans are over age 50. Among over 50 fans, 40% prefer Iron Man. Among under 50 fans, 60% prefer Iron Man. Now, suppose you meet a fan who says Iron Man is their favorite. What's the probability that this fan is over 50? Step 1, find the total probability someone prefers Iron Man. The first group is over 50, and their proportion is 0.3 times 0.4, the probability of over 50 person preferring Ironman, plus 1 minus 30% gives us 70%, or 0.7 for the second group, under 50, times 0.6, the probability that the under 50 group prefers Ironman. Then, there we go. Step 2, we're going to apply Bayes' rule. So the probability that they are over 50, given they love Ironman, is 0.3, the probability they're over 50, times 0.4, the probability they love Ironman, divided by the total we got in step 1, which is the probability of a fan loving Ironman. So there's about a 22% chance that an Ironman fan is over 50. Notice how we're updating our estimate based on what we've seen, that they prefer Ironman. Here's a more serious example. Suppose a rare disease affects 1% of the population. A test is 99% accurate. It gives a true positive 99% of the time, and a false positive 1% of the time. You test positive. What's the probability you actually have the disease? Well, we need to consider both paths to testing positive, right? So if we have the disease and test positive, we'd have 0.01, the probability that we have the disease. That's a 0. Times 0.99, the probability of a true positive. So if I multiply that, that gives me 0.0099. Now the probability that we don't have the disease would be 0.99. That's the probability we don't have the disease, times the probability that we test positive, which is our false positive rate, the 0.01. So again, that's 0.0099. So both probabilities round to 0.01. Now the total chance of testing positive, we'll add those two together. And Bayes' rule gotta erase my writing here that's in the way. There we go. Even with a 99% accurate test, you only have a 50% chance of actually being sick. That's because the disease is so rare. This is why doctors often follow up with additional testing. Initial results on rare conditions can be misleading. Sometimes it helps to visualize what's happening, like with this pie chart. One slice represents people who have the condition and test positive. Another slice represents people who don't have the condition, but also test positive. The Bayes numerator is just one piece of that, the piece we care about. The denominator is the total positive tests. You can also think of this like filtering. Bayes' rule filters the total sample space down to just the relevant slice, the ones that both triggered a condition and fit a group. It's a precise lens for answering questions like, among the people who tested positive, which ones actually have the condition? All right, let's wrap up. Bayes' rule is used whenever we revise probabilities based on new information. The law of total probability helps us get the full picture of a situation. Bayes' rule flips conditional probabilities to help us interpret clues. Applications include medicine, email filtering, fraud detection, customer profiling, and more. Even outside of data science, you use this intuitively every day, updating your guess about who's texting you based on the tone, revising your confidence in your fantasy football team based on a new injury report, or deciding whether a mystery character in a trailer is a villain or just misunderstood. Once you've mastered Bayes' rule, you'll start seeing it everywhere because it's how humans and smart algorithms learn to update their beliefs. And by the way, I didn't prompt AI for capybaras this time. It just knows my style. Of course, the image is total nonsense and unrelated to our topic, but when I saw the cappies, I just had to use it. I do worry about the probability of a Belsing to each subgroup, though, whatever that may be.